So the first presentation I want to show you is about um, this two-step design of negative feedback amplifiers. So the negative feedback amplifiers consist of two elements. You could say it's a feedback network, and that feedback network fixes the ideal value of the transmission one parameters of the amplifier. We have designed it in a previous stage. And we have controllers, and controllers nullify the errors between the source quantity and the copies that we generated of the source quantities in the feedback networks. So that is for minimizing the errors. And that makes us also come to the two-step design. First, we are going to design the feedback networks and using nullers as controllers, and then we need to design the controllers. And in this course, we are not going to design controllers, we are going to select controllers, operational amplifiers as controllers. But in order to select something, we need to know what specifications of those op-amps should be. And that's what we are aiming to find in this lecture and the next lecture. So the error budgets for the whole amplifier thus must be split in two: the budget for the feedback network and the budget for the controller. So let's first discuss errors that we can expect from the feedback network. So the feedback network, and let's then study the bandwidth and the noise and the linearity, those important aspects. So we have seen that passive feedback networks enlarge the contribution of controller noise to the total amplifier noise. You remember hopefully now that for example, the feedback resistors in a non-inverting feedback voltage amplifier appear, the parallel connection of those two appear in series with the source for their noise behavior. And if those elements are dissipative, so have a real part, then they contribute noise themselves. That's they also do the other thing, but then they also contribute noise. So let's study the next one, the power efficiency. Well, it's more or less the same. We have seen that passive feedback networks, they require the controller to deliver more voltage or current. So they enlarge the power losses in the controller. And if those impedances have a dissipative part, so if they have a real part, then they dissipate power themselves, and this also contributes to the power inefficiency of the amplifier. The frequency response. Well, we could use, instead of resistors as feedback elements, capacitors and inductors in feedback elements, and those then determine the dynamic characteristic of the amplifier. So basically, since the transfer from source to load of an ideal feedback amplifier is the reciprocal transfer of its feedback networks, the poles and zeros in the feedback network become zeros and poles in the amplifier's transfer. That is basically what will be happening. Nonlinearity. Well, if the feedback network is nonlinear, then we get a nonlinear transfer. So if you want to have an amplifier having an exponential input to output relation, you need a log element as feedback element, because you basically get the inverse transfer from that of your feedback network. Temperature stability and aging. Well, if your feedback network changes over time, if the values, the transfer changes over time, then the transfer of your amplifier, of course, will also change over time. So there can be all kind of error contributions from the feedback network. And these are the most important. Let's go to the controller and see what kind of limitations we can expect, contributions to limitations we can expect from the controller. And the question that we want to answer here is, in which way and to what extent do performance limitations of the controller contribute to those of the amplifier? So if the controller has equivalent noise sources, then we have already seen how they affect the noise behavior of the feedback amplifier. But what if the controller has a limited bandwidth? or if the controller has a nonlinear but shows nonlinear behavior. That is important. That is what we want to find out. But first, let's make an inventory. So for this, of course, we need a model. We don't have yet a model to describe that. That is what this is about. So the model that we want is, it should describe the transfer as the product of the ideal controller, so only determined by the ideal transfer, only determined by the feedback networks, with nullers as controllers, and some kind of function that tells us the influence of controller performance limitations. So then let's make an inventory of these kind of limitations. So what can be reduced by feedback? Basically, what are the error reduction capabilities of negative feedback? Well, gain accuracy, inaccuracy, and drift of the gain, bandwidth limitations, and weak nonlinearity can be cured with negative feedback, because if the feedback network is linear, instantaneous, and accurate, the ideal gain will be linear, instantaneous, and accurate. And only the controller might contribute something, but if the controller is another, the contribution is not important, because then we have the ideal gain. So the error reduction capabilities of negative feedback are these performance aspects. What not can be cured with negative feedback is noise contribution of the controller. The feedback amplifier cannot distinguish between noise coming from the signal source and noise coming from the controller. It just treats them as the same. And we have already seen how we can deal with noise of the controller. This, like this voltage amplifier, I told you before, the feedback resistors appear for the noise as if their parallel connection is in series with the source. The voltage and current drive capability of the controller. Well, if the controller is clipping, it's not doing anything anymore. So let's say there is no feedback anymore. So then the amplifier will be clipping as well. So the voltage and current drive capability of the controller cannot be improved with the aid of negative feedback. Biasing and offset errors, as we have seen in the previous lecture with biasing, are basically the same as noise errors. It's only, let's say, a distribution over an ensemble instead of over time, but you can treat them in the same way as we have seen. So biasing and offset errors of the controllers are not reduced, the influence of those errors not reduced by means of negative feedback. So, and then we have a few things that may be questionable. What about parasitic impedances between the controller terminals and ground? How do they affect the transfer? Well, this is something we will study in specific examples, and there are also some examples in the book. So this is the first presentation.